The cell starts at its resting membrane potential. Sodium is much more concentrated in the extracellular fluid than in the intercellular fluid. Potassium is much more concentrated inside the cell than it is outside the cell. Potassium leaks out through passive transport, and sodium leaks into the cell through passive transport. But the sodium-potassium pump, which is active transport, compensates by pumping 3 sodium out for every 2 potassium it pumps in. This establishes the resting membrane potential of negative 70 millivolts. Action potentials can be generated in areas of the neuron where there's a high density of voltage-regulated gates, also called the trigger zone. Step 1. A local potential depolarizes the membrane. Step 2. The local potential reaches threshold around negative 55 millivolts. That is the minimum needed to open voltage-regulated gates. After threshold is reached, the neuron can now produce an action potential. Boom! Voltage-regulated sodium gates open quickly, allowing sodium ions to rush into the cell, further depolarizing the membrane. As the membrane potential passes 0 millivolts, sodium gates begin closing. The voltage peaks around positive 35 millivolts. This means there are more positive ions inside the cell than the large negative proteins that cannot escape. Step 5. Potassium ions, repelled by the positive intercellular fluid, now exit the cell. Their outflow repolarizes the membrane back into the negative numbers. Step 6. Because potassium gates stay open longer than sodium gates, the membrane voltage drops lower than the original resting membrane potential, producing a negative overshoot, also called hyperpolarization. After hyperpolarization, the cell returns to the resting membrane potential with an intercellular fluid versus extracellular fluid membrane potential of negative 70 millivolts, maintained by the sodium-potassium pump.